In this section of 13.4, we're going to be looking at propagated and relative error. Given z is a function of x and y, differential x is equal to that incremental x, and differential y is equal to that incremental y, your delta x and your delta y. Your total differential dz estimates the propagated error of which is delta z, the incremental error, and dz is approximately that delta z. dz divided by z estimates the relative error, which is the actual change in z divided by z. So this is an approximation. To apply this, we're going to be looking at the volume of a cylinder, and suppose we're constructing cylinders, and the radius of the cylinder is supposed to be 5 centimeters, but there is a possible error of approximately 0.01 centimeters. So it could be a little bit more than 5, a little bit less. That error is about plus or minus 0.01. The height of that cylinder is supposed to be 5 centimeters with a possible error of plus or minus 0.02 centimeters. So it could be a little bit taller, a little bit shorter than what it's supposed to be. We're going to use dV to estimate the propagated error in the volume. So let's take a look at this. So here we have the volume of a cylinder, and what I've done here is I let the radius is equal to 5. Now that possible error, we're going to use the differential dr to denote that possible error of plus or minus 0.01. The height is equal to 5, and we're going to let dh, that differential height, equal plus or minus 0.02. We're going to use dV to estimate the propagated error in the volume. Well, you know that dV is equal to since volume is a function of r and h, it's the partial derivative of the volume with respect to that first variable r times the differential r times the partial derivative of the volume with respect to h times dh. That's your total differential. The partial derivatives times the differentials, add those together. When we take the partial derivative of volume with respect to r, you treat r as the variable and you treat h as a constant. So we know the derivative of r squared is 2r. So the derivative of this is going to be 2 pi rh times your differential r plus the partial derivative of the volume with respect to h. You treat h as a variable and r as a constant. So the derivative of this constant times h is that constant times your differential height, dh. So now this is our total differential dV. We're going to plug in the values that r and h should be along with the differentials of r and h. When you plug those in, r is 5, h is 5, and dr is plus or minus 0.01. And again, plugging in plus or minus 0.02 for dh, we see that we could simplify this. 2 times 5 is 10 times 5 is 50 times plus or minus 0.01. We get plus or minus 0.5 pi here. And then 5 squared is 25 times plus or minus 0.02. We get another plus or minus 0.5 pi. Now, if both of these are positive, then you have the largest that the volume could be estimated to be is a plus 0.5 and a plus 0.5. So it could be up to actually 1 pi altogether. And if these are both negative, then it's could be off by a negative pi. Now, if one's positive, one's negative, then you can either have like plus or minus point. You could have 0 actually. So that 0 is in between that maximum and that minimum. So we don't need to consider the case where one's positive and one's negative, because this plus or minus pi goes everywhere from a negative pi to a positive pi. It covers those possibilities. So plus or minus pi is your estimate for the propagated error in the volume. And this is approximately 3.14. And when you're measuring volume, you're using cubic units. Since we're given centimeters here, the volume could be estimated to be off by as much as about 3.14 cubic centimeters. So we want to now estimate dV over V. Use dV over V to estimate the relative error. The way you do that is you take your differential volume, which we already found, dV to be plus or minus pi, and you're going to divide that by what the volume should be when the radius is 5 and the height is 5 exactly, without including the errors. We get that that should be pi times 5 squared times 5, which will give you plus or minus pi divided by 125 pi. Again, that could be simplified to plus or minus 1 over 125. You can write that as a decimal, approximately plus or minus 0.008 or about 0.8%. So not quite a 1% possible error in the volume. And that's our estimate of the relative error. In this example, we're going to use differentials as an approximation. Use a differential dz to approximate the change in this function z equals square root of 4 minus x squared minus y squared as xy moves from the point 1, 1 to the point 1.01 and 0.97. So we're using differentials. Total differential dz is going to use dx and dy. So we can look at these points to determine your dx and dy. That's going to be your incremental change in x and your incremental change in y. Going from 1 to 0.01, that incremental change in x is 0.01. And going from 1 down to 0.97 for the y is going to represent an incremental change in y of a negative 0.03. So again, that's how we get our differential x and differential y. Those are the incremental changes in your x and y. And we're going to use dz, that total differential dz, to approximate that incremental change in z. To find dz, you're going to take the partial derivative of that z function with respect to x times dx plus the partial derivative of z with respect to y times dy. When you take those derivatives using the chain rules, we get this as follows here. That's going to be your estimate of your incremental change in z. Now we want to look at the point where x is 1 and y is 1, and your incremental change in x and y are 0.01 and negative 0.03. When you plug in those values, you get that the incremental change is approximated by your total differential, which is approximately 0.0141. That's an estimate as to how much z would change if you change your x by a plus 0.01 and your y by a negative 0.03. If you started out at the 0.11. So that's just an estimate of how the z is going to change. To see the exact change, you compare the heights at the 2 points. So at the original point 1, 1, plug in 1 for x and 1 for y back into the original function, you get a value, and you plug in that new point, 1.01 and 0.97, into that original function and look at the difference. That's the actual change in the z. That's the incremental change in z, is 0.0137 approximately. So you can see that total differential was an estimate of this change in z.